The two topics I'm covering today, compartments and ports, are brand new to version 5.8. So if you haven't heard about these before, that's the purpose of this talk, is to introduce you to these. This is not training. This is going to be just an overview of what these new elements are and how to use them, the kind of applications you should be thinking about using them. They are quite complete and complex. I'm just a little bit excited about them too, because this is something that has been in progress for 2 years before 5.8 was released. It's taken quite a bit of time, and it's very unusual, as I hope you'll find out or discover. And that's what I mean by this next slide here, between two worlds. Basically, I don't think you'll have ever seen anything quite like this before, and I'm hoping that it fills a gap in our capabilities. And the idea is that this is a tool that's intended for partially filled vessels, which sounds like a very complicated way of saying a half-full tank, but of course, sometimes it isn't a tank. If you're a user of Cinefluent and FloCAD, you know that tank has another mathematical meaning, so we tend to try to use the word vessel in place of that. And half filled, well, it could be a quarter filled, three-quarter filled. So we end up with this much more complicated way of saying things, a partially filled vessel. But what we're intending the application for this to be are things like oil and fuel tanks, boat, aircraft, automotive, liquefied natural gas tanks, and other sort of cryogenic applications like cryostats and Dewars, or if you're into liquid propulsion, launch vehicle fuel and oxidizer tanks. There's just a lot of times when we have a fairly complex tank that's partly full and it's the focus of our model. And what I mean by in between two worlds, I guess before I mention that, I should point out there are other applications that you might not think of as a tank, but are really kind of a partially filled vessel, such as a boiler, steam generator, or as I'll show you in a moment, immersion-cooled electronics. Basically another kind of half-full vessel, but in this case, it's always half full. It's not filling or emptying or draining or venting or anything like the other ones are. So what I mean by in between two worlds, the CFD codes are getting better, computers are getting better, but it's going to be a long time before they're capable of modeling systems like I'm going to show you. And part of the reason for that is they are geometrically complex, but another reason is that an awful lot of time we need to be analyzing transients for long timescales. And all those things, complexity, two-phase, boiling, condensation, long-term timescales, all that kind of stuff makes it hard for a CFD program to get very far. So they haven't been used a lot for that. On the other hand, the fluid network approaches, such as we're providing in FloCAD, Cinefluent, and so forth, really have a struggle themselves too, because these are geometrically complex walls, internal structures, and so forth. And a fluid network approach is a 1D tank pipe sort of code. So teaching it to understand the complexities of complex volumes, walls, structures, and so forth has been the trick. So what we're going to present is between these two worlds of pure 3D and pure 1D. And it's probably easiest to explain that in terms of an application. So let's look at a marine fuel tank, a gas tank on a boat, basically. And this one is got, I think it's about 2 feet wide, maybe a foot and a half tall, and maybe about 8 to 10 feet long. I honestly can't remember all the dimensions. And it's sheet metal that's been bent and riveted and so forth, and of course welded on the outsides. And I've taken the top off here so you can see inside, and you can see that there's two, oops, got ahead of myself there. You can see that there are two baffles, one here and one here, and those are basically intended to control slosh for one thing, to make sure that if the boat's really moving quick that the fuel doesn't splash too much, but also of course it's a structural purpose of keeping the tank rigid in the places where it needs to. But it's got fairly large holes, as you can see, and you can see the fluid here is shown transparent, and you can see it intersecting baffle number 1 here, baffle number 2 here. And this line across it, if you can notice that, is actually where the fuel is touching the top of the tank, which, as I say, has been removed. So this gets you an idea of the complexity of the situation. Here's a slightly different example where it isn't this, just a tank that's sitting still with the liquid level equilibrated between all of these 3 zones, but it's actually a different zone. It's flowing between these zones. And of course, you see this line here. It's touching a larger part of the surface here. So this is the kind of problem we're going to be attempting to analyze with compartments and ports, and I'll show you this in more detail later. But for right now, I'm just trying to get across the idea of the kind of applications you might attempt with these new tools. For example, what if your design question is, here's the outlet here, what is the temperature of the fuel that's going into a pump during the voyage? So this isn't just a single steady state sort of analysis. This is a long-term transient with motions and so forth, a very complex situation, and you're asking to track the fuel temperature during the entire event. And that's something that is basically more than a traditional simple fluid network could handle, but it has to be less than a CFD code. Of course, a CFD code could handle that, but if we had launched it off a couple years ago, it still might be solving. It's a very complex problem for CFD. And the trick is that a lot of times for applications such as this was designed, you don't just analyze one event, you analyze hundreds and possibly tens of thousands of these events. And so you need something much, much faster. Okay. So here's another example of an application is a Dewar, or cryostat. This is actually a picture of NASA's Gravity Probe B, the Dewar. This was testing Einstein's theory, I believe. I'm not a physicist, but from a thermal fluid perspective, if you look inside this thing, this is a 2D model of it, you can see there's a lot of complex structures inside of this Dewar, which was, I believe, a liquid helium Dewar, and it has a vent here where the boil off comes out and forms a complex shield, which isn't really shown here, a vapor-cooled shield. So we have a lot of structural and fluid complexity, but once again, to do a cryogenic system, you either have to find a clever way to work in steady states, or you have to work in transients. And of course, on ground, where secondary flows and so forth might form, it's going to be a very complex fluid system too. So once again, it's somewhat in between CFD and flow networks, right in the hopefully the sweet spot of compartments. And of course, that's the key here, is being a Dewar, being cryogenic, it's going to take a long time to get to an equilibrium heat flux and heat leak. Another example is if you have boiling and condensing over complex structures. And I could show pictures of boilers and steam drums and systems like that, but something that I think is a little bit more interesting is immersion cooling. This is where you actually drop your PCB boards into a dielectric fluid and let it boil, and the vapor comes up and condenses on the coils and falls back down again. This is actually does exist, and we'll have some papers and examples on this soon that include some references if you want to go chase them down. Here's an example, for example, from 3M of the boiling going on in between these PCB cards. And I'd recommend you go search on YouTube for some of the cool videos of these things. If you've ever worked electronics, to watch an electronics board sitting inside of a liquid boiling is just kind of scary and awe-inspiring. I'm not sure. Someone was asking, what are these colors in here? My guess is someone put lights in here to make a cool video because it's not glowing red. That wouldn't be a successful design. So what has this got to do with compartments? Here's an example of a compartment. In this case, we moved this is actually just kind of a diagram. You don't put the condenser coils above the boards, so you slide them out of the way. So these are the condenser coils here. This is a liquid surface, and these are the boards boiling away inside here. This is a compartment, as we'll show you in a minute. the GPUs, actually, they're not CPUs, but graphical units, 8 kilowatts total in one of these tanks. It's a lot of power. And as I said, the condenser tubes, and then this plane surface here is a liquid vapor surface. It's green right now, which is this color here, 49 degrees C saturation temperature. Another completely different example is a glass geyser. This is a system. I think it's you can see this 1 centimeter diameter to give you an idea of the scale. A couple foot tall glass geyser. I'll show you a picture of it in a second. The idea is some volcanologists, which is what the people who study geysers are called, are trying to figure out the influences of a bubble trap here, the reverse flow zone, when this chamber down here starts boiling. The idea of this geyser is to try to figure out the strange frequencies that happen in an actual geyser and trying to figure out what must be going on underneath the ground to try to explain this. And here's a picture of it where they're boiling away. This chamber starts boiling and then eventually shoots vapor up here. I'm sorry, it shoots the liquid in the tube up here. Vapor gets trapped inside the bottom here in the trap and comes up with some odd oscillations. So we make a model of it. This is a TD model of it, a fairly crude one. We're just kind of playing around right now, but it shows the lines. And guess what? Those two reservoirs here become compartments because we're talking about partially filled vessels, right? And not only that, we care about where the entrances and exits to these are, because as you look at this, this entrance to this pipe here is at the top of this little compartment. This other one's down here hidden underneath the insulation or water layer, whatever it is down here. And this one's interesting because this is the geyser that comes shooting up in the middle of that reservoir. So how do we explain that to the code? We use ports, which we'll be talking a little bit more. We say this is the location at which this pipe connects to this compartment, and this is the location where this pipe connects, and this one is actually inside of this volume. I could draw an arrow over here, but it would just look like I'm pointing at the volume there instead of the inside. So a port can be on the edge and it can be in the middle, but it's a way of telling the code where the entrances and exits are to these compartments. So with that, hopefully you have enough to be introduced to what a compartment looks like. So I'm going to talk a little bit about how you build them. Very simple terms. This is not instructional. I'm not going to be able to take you step by step through how to build one of these, but just the elements that are available to you or the steps that you need to take. First of all, as you saw by those examples, what is a vessel could be very odd shaped. So you need to define an arbitrary volume and say, this is my fluid volume. And in fact, that may contain what we call bays or subcompartments. And I'll talk a little bit more about this later. Some of the compartment examples I was showing you don't have any subcompartments, but a couple of them do. And why you would use those, I'll show you later. And of course, you can also define complex thermal structures. Now, it can be just the walls. You can say, well, I've got a tank, here are the walls. But in some of those examples I showed you, we don't even care about the walls, such as the immersion cooler example. We knew what the shape of the volume was, but we didn't really care about the walls themselves thermally. But there was internal components, such as the PCB boards or the condenser tubes inside, that we do care about. So when we say thermal structure, it doesn't have to be the vessel walls. It could be all sorts of things inside, boxes, tubes, baffles, and so forth that are inside of the fluid volume. As you might imagine, there's a lot of different physics going on here. It could be boiling, could be condensing, could be natural convection, it could be flow over a tube in some cases, or condensation onto a tube, or heat transfer from a vertical surface on one side of a box and from horizontal surface on the other side of it. So within a compartment, there could be a lot of interesting things going on. It does have a default setting. It will build the heat transfer for you, but you have extensive ability to get in there and change it, customize it, and modify it. And then finally, the fourth part of it is the ports. Where are the vents, the drains, or other fluid connections? It doesn't have to be on the wall. It can actually be inside the compartment. And in fact, this could be a connection between two compartments. And I'll give you an example of that in a minute. Here's the key of the compartments. We talked about this is more than what you're used to seeing in a flow network or 1D thermal-hydraulic network modeling system. It's a lot less than what you'll still see in a CFD code, of course, because the entire purpose of compartments is to run very, very fast. The orientation, the fill level may vary during a run. The fluid can move around, but it's still not CFD. I have to emphasize that because I'm going to show you some videos here, and you might start to think, wow, I'm actually watching a CFD solution, but it's not. These whole things are meant to run in minutes, not hours or days. And in fact, if we can get away with it, seconds, because a lot of the applications this was intended for, as I said, need to run full hours-long transient scenarios in less than 3 minutes total. So let me go back. I've shown you these three pieces, the volumes, the walls, the heat transfer and connections. I'm going to talk about each one in turn here, starting with the arbitrary fill volume. This is the volume that we were using for that immersion cooler. You see it's kind of rectangular. There's actually a slanted surface here. So it doesn't look very complicated, but it's certainly not a cylinder and it's not a rectangle either. This is a more typical example of the kind of thing we'd expect a compartment to be able to handle. This is actually a LNG or liquefied natural gas tank where it's got ribbed walls, it's got baffles in the middle of it, anti-slosh baffles. In this case, it's a horizontal tank compared to what you might be used to. And this is just a simple sphere. Now, a simple sphere is shown here because I can show you a movie, in this case, very easily of, this is also an LNG tank, by the way. This oval, if you look here, is actually the liquid surface. And what you're going to see as we're executing this is it draining. But not only is it draining, but we're rocking back and forth. This was intended to be like an LNG tank on a ship or a train. And you can see the motion as it slowly drains from the bottom here and the wall warming up during the event. And this is only about a 5-minute transient here, so it's a fairly quick drain. But as I'll show you, the system is meant to be run for hours long if you need it. Okay, so this is the kind of volumes you have. Everywhere you have the gravity direction, you have fill levels, and anything you've defined in here will be intersected by this liquid vapor plane and either considered to be wet or dry as a result of that. So let's get to another capability of compartments, which is the bay. Let's go back to that fuel tank and look at it and say, well, there's kind of 3 zones here, right? Are there 3 complete separate zones, or is it really just an obstruction, just something in the middle of the flow? If this had been a very minimal structure, you would have seen that, yeah, the fluid would have moved back and forth really quickly between those, and I can almost ignore that structure. But as those holes get smaller, it really is a more physical subdivision between the zones. And to illustrate this, let me look at the volumes associated with each one of these. I've made this volume transparent, this one highlighted, so that you can see there's 3 volumes corresponding to each one of these zones inside the tank. And I'm going to talk about these in relationship to a compartment. Is this 1 compartment or is this 3 compartments? So the question you'd ask yourself in this case, does the flow move back and forth quickly between these zones? Does it take its time? Are the holes so small that it takes time to slosh back and forth? And if it does take time to move back and forth and there's 3 distinct zones, then is it possible for there to be a unique liquid surface in each zone? In other words, it's not moving so fast, there's actually a height difference between each zone as it's draining or filling. And is there a unique air or fuel temperature in each one of these zones? Maybe there's a hot surface over here, but not over here, that might tend to drive it to have a gradient within the fuel itself. If there is no such gradient, if we can assume it moves back and forth quickly, then this is one compartment. Even though there's three separate volumes here and they don't even have to touch each other, we can say that is one compartment, but I can still subdivide it into what's called a bay. A bay is a subdivision of a compartment, or a subcompartment, if you will, that has its own unique heat transfer environment if they're kind of separate but not completely. Okay? Versus, no, I really need to have it three separate compartments with no subcompartments in each one of them, and I need to now define the flow between them because these are three separate temperatures, pressures, liquid levels, and so forth. If I just let it run, but I didn't define any openings between them, then this one would drain and these two would stay full. So I have to, in other words, describe these holes. How does fluid move back and forth between these? So I want to first show you an example of a compartment with three bays. So this is the result of assuming that I have one surface. You can see it here. So the liquid is transparent right now. You're actually looking at the liquid vapor surface. You can see it just cutting right through that middle baffle there. And you can see it's one temperature. It's 60 something degrees down here. It's one temperature cutting right through them. And you'll see I don't even have holes here anywhere. It's as if they were permeable walls. These little funny things here are actually ports. I'll talk about those in a second. But right now there's really only just a vent and a drain port. And this will become clear in a minute. So let me go ahead and execute this. You'll notice this is a drain event as the boat is rocking back and forth and going for hours. I think it's about a 1 hour transient total. It only takes a couple minutes to solve. I've stopped this one here short at just a tenth of an hour or so. But again, you can see one temperature cutting right through. It doesn't mean I can't have customized heat transfer in each one of these bays, but it's one liquid surface, and I don't have to worry about how flow got between zone to zone. All right. And you'll also notice the very coarse modeling. Look how coarse these nodes are. I have basically one element that's moving the entire height of the bay. These are the finite elements that describe this wall. Very, very coarse. And I'll talk more about that in a minute, but I just want to show you for right now the kind of level we expect when running this. This is now a comparison analysis, and there are three compartments in this, so three different liquid levels, which will become clear as you watch it drain. Very clear that there's three completely separate liquid levels in each, and that flow has to be moving back and forth between these holes. So in other words, at this point, flow would be coming waterfalling in through that one compartment and landing in this other compartment. And it's a little bit tough to see, but you can see if you look carefully that there's three different temperatures associated here. But these little conical things here, these ports, this is the vent port, and this is the drain port. But look here, there's also some extra ports now that have appeared between the walls. So these are the ways in which fluid gets back and forth between those compartments. And that's a nice lead-in to what the heck is a port and why do we care? Basically, the purpose of a port is to tell the code, this is my entrance or exit location. Am I submerged or exposed? So just the same way we're worrying about, is the wall wet or dry? You can think of it as the opening to a pipe or a flow path. Is it wet or dry? That's handled basically by a port. So looking back at our boat tank example, this is actually on the top plane. So this is a vent here on the top. This is actually a submerged inlet. So there is no hole at the bottom of this tank. There's a hose that comes down through the top, and that's the opening of the hose. But then here's the holes between each of these compartments. So this is the three compartment model, and I have to define, these are not the holes themselves, these are the locations of the holes. The holes themselves I would have to model separately by saying, well, that's an orifice, or that's some K factor or something like that. But the purpose of a port is to locate it within three space. And that includes as the tank moves and shifts, and as the liquid surface level moves and shifts. So again, that's the vent on top. These are the holes between the baffles. Because I've got a three compartment model, I would not need those again if I had said, oh, the fluid moves fast enough, I'm just going to model it as one compartment and three bays, then I don't need those holes. And there's my submerged intake. I noticed that for the folks signing up for this webinar that most of you are familiar with Thermal Desktop, and I would assume familiar with FloCAD. So this is a little bit of a tangent on this page, but I want to point out, since the title of the talk was Compartments and Ports, ports don't always have to deal with compartments. They can actually stand alone and be useful in and of themselves. One very important use of them is a port not on a compartment, but on a pipe. So you can actually not just point to a compartment, you can actually point to a FloCAD pipe. Why would you want to do that? Well, if you have pointed to the side of a pipe and said, here is where my opening to that pipe exists, then if the resolution of the pipe changes or the pipe moves, you've still got that hole in the pipe basically where side flow can come and go. So very convenient for a lateral on a manifold, for example. If you happen to be familiar with flat front modeling or prime purge modeling, side passages actually know where the front is within the pipe. So in some ways, it's kind of like a mini compartment, or a long, thin compartment is a pipe. The ends of a pipe actually could also become a port, and the purpose of that is to be able to join pipes end to end. And an example I've kind of already showed you is how to connect a pipe to a compartment. So these two pipes here, pipe 1, which is the actual geyser tube, and pipe 2, which is the return tube, you'll notice they start and end with these little red cones again. Those cones are pointing, by the way, to the center of the compartment where the lump currently lives. And they are telling it that, hey, this is where this connects to that compartment, and this is where this pipe connects. So the ends of a pipe here have been turned into ports. If you're using FloCAD, you'll know that they start out as junctions. In prior versions, you can actually change them and say, no, I don't want a junction, I would like it to become a port. And the real reason I'm emphasizing this is that in the past, version 5.7 and earlier, if you wanted to do things like this, you had to connect or disconnect pipes. And as you might have learned, once you do that, you can't change the resolution. To change the resolution, you have to disconnect it, change the resolution, then reconnect it. All of that's gone now. So I'd really strongly recommend, if you're a pipe user, to check out ports, even if you have zero interest in a compartment. I don't know how you could possibly have zero interest in a compartment. They're just so cool. But if you do, take a look at pipes. Okay, back to compartments. I pointed out the very coarse resolution in that wall for the fuel tank. And that's because we've done an awful lot of work trying to make sure that you can have very coarse walls and get the right answers. We don't have to mesh the heck out of it. So in this example, this is the liquid vapor plane cutting across a finite element surface or structure. And this is a fairly fine resolution, but that's okay. It teaches the point. It's intended that when we're executing these, we're moving at very high level, system level transients and need to do the entire boat, airplane, aircraft, or launch vehicle, whatever it is. We need to do the entire thing very quickly. And that means that we have to be able to handle very coarse models. So it's very easy to look up here and say, hey, this node up here is 100% dry, or this node down here is 100% wet. But the key to being able to handle very coarse resolution is to be able to look at this node and declare it to be 63% wet. So in other words, it will see part of the liquid and part of the vapor, such that when you're analyzing this, you don't see a funny contour. You see the sharpness, almost as if you were subdividing these elements, will appear. And here's an example of one that's above. And you might look at these and say, hey, this is below the surface, shouldn't it be 100% wet? And this is above the surface, shouldn't it be 100% dry? Well, remember, this is finite elements, so it's actually the function of all of the elements of which this node is a member. And in this case, it knows that it's got a fraction of these surfaces. This is cheating a little bit because when you analyze this element, it knows that it's kind of far away from the surface, and it knows that this element is essentially 100% dry, this one's partially wet, and so forth. But the point is the code is able to come up with a way to discern the wetness or dryness of each section, with the entire purpose of being able to handle very, very coarse models. Okay. Let me show you some other examples. This is dropping a wrench, a hot wrench, into either oil or water. And the purpose of doing this is to demonstrate not just the different modes of heat transfer, the different kind of heat transfer that's available to you and ways to override it and so forth. This is also to show you that a compartment doesn't have to look like anything like I've been showing. In this case, I'm dropping a wrench into oil, and you can see this gray box back here. That's actually the compartment volume. In fact, if you look carefully here, you can see a port, which is how it vents out. And here's the liquid surface coming up here. So in other words, instead of dropping the wrench in oil, I'm actually holding the wrench still and raising the liquid level in an oil-filled compartment. Okay, and if we watch that happen here, you'll see that, and in this case, I went very, very slowly. No one would take 100 seconds to drop a wrench into oil, but in order to see some nice movies and trends and so forth, I had to drop it slowly. So this is for the sake of explanation, not demonstration. And you can see, of course, that the wrench has nice smooth gradients up as it's being dipped into the oil. And we're going to contrast that with dropping it into water. This is convection oriented. There is no nucleate boiling in oil. When we drop it into water, and this is a 200-degree wrench dropped into 100-degree water, a heck of a temperature gradient there, and you're going to see boiling happen. And because of that, you're going to see a lot more excitement. In fact, we drop it quicker into the water to just demonstrate the concepts. And I went ahead and showed the finite element resolution here. It's much more coarse in this model, but in this one, I went ahead and made it fine because there are strong temperature gradients going on. Just because compartments can handle coarse gradients doesn't mean that's what you should use in your model if, in fact, there's very sharp gradients going on. So let's go ahead and run this movie, and I think you'll see what I mean. Now, notice how there's a lag here. It doesn't even look like it's dropped into the water yet, and then suddenly, there's a quench line forming here. So this is what you're looking at here is everything above this red zone is film boiling. There's basically very little heat transfer going on because it's a film of vapor surrounding the wrench. It's too hot. It's not formed nucleate boiling yet, so it hasn't been able to remove a lot of heat. Here, it's formed nucleate boiling, so you get a very sharp gradient in that wrench as you drop it. Okay. There is no wall here. So the purpose was that the compartment can focus on something inside the compartment, such as the immersion cooling example in this wrench example, or it can focus on something on the wall, such as you would do for a Dewar or the fuel tank. Okay. So I've talked about how this is more than what you're normally used to seeing in 1D flow networks, but of course, the trade-off is this is not a full CFD solution. And if that's so, there's going to be a lot more unknowns and approximations going on. So we have to pay somewhere for the fast speed. And we do so in approximations and uncertainties and so forth. There's, of course, uncertainties in any analysis, including CFD, but a few more here in exchange for the very fast solutions. So the idea is that you should be able to bracket and you should be able to run a lot of times rather than running once and trusting it. So in order to allow for the fact that there are some uncertainties in any of these kinds of analysis, we have conservative or safety factors that allow you to push the uncertainties to one side or another. In other words, if I'm trying to find the hottest fuel temperature that comes out of that boat tank, I can put in a factor that says, when in doubt, skew it towards that answer such that I know I have a conservative answer. There's also geometry correction factors. And this is more for the natural convection or single phase convection sort of things. When you're dealing with boiling and condensation, it doesn't care as much about where you are. It just really cares about the local wall state. So that's fortunate. But if you are doing natural convection, and that would be true in a lot of the non-volatile fluid tanks, then it's important to know where you are in that tank and is a single convection factor really adequate. And to illustrate this point, I'm going to assume we have a cold fluid inside of a hot wall, kind of an ovoid cross-section here. And what you'd expect in a case like this is that if you had one heat transfer coefficient predicted for this entire vessel, that it really would be a little higher at the bottom where there's hot beneath cold and plumes would form. There's a lot more driving force here for augmented convection here, whereas up here, it's going to tend to stagnate. So there would be a kind of a local stagnation formed, and heat transfer and convection would be degraded up here. So to account for that, there's additional factors that say, hey, as a function of where you are, and it doesn't have to be a sphere or anything like that. It's basically done by figuring out what the angle is between the acceleration vector and the current surface. But you have a way to basically adjust and say, hey, go ahead and augment the heat transfer at the bottom and degrade it at the top as a function of actually the dot product between the surface normal and the acceleration vector. What does that look like inside a compartment form? And this is as close as we're going to get to what's inside the code. This is a compartment edit form. It looks huge because there's a lot going on here. This is one compartment, and it has one bay. So if I wanted to add another bay, I could come over here and click a button and say, okay, this is subdivided into additional bays. But a lot of the compartments you'll be working with will just have one bay in it if there's no natural subdivision going on. Within that, you have the list of solids that will represent the volume meshes. So in other words, all the things that will describe the volume of this. It may be just a single solid, but as I showed you in that boat take example, you can sum up a lot of little solids, or, you know, I hate to use the term solid because that's just a TD term. It's really volume. So whatever the volumes are that you're summing up describe the fluid shape. Similarly, all the surfaces that describe this, are they walls, are they internal, whatever surfaces you want inside there will become surfaces for this bay. And you'll see there's another tab here for additional ties in addition to all the ones that are naturally built per bay. There's also radiation. I haven't mentioned this, but there's actually a fast solving radiation solution that can march in lockstep with your liquid level. And the purpose of this is if you have a cryogenic application, or even, you know, we've had people that didn't have cryogenic applications that just had a very hot temperature or were very sensitive to heat leaks at the top, you can actually include simplified radiation as part of the solution. You can include obstructions such as this list of volumes over here is nice, but there's actually boxes, tubes, baffles, ribs, something that take up some volume. So you can reduce the volume by what's called a packing factor. So packing factor of 1 means this entire volume is active. Packing factor of half means that half the volume is obstructed by something else. These are the safety margin factors you have. Do you want to err on the side of too hot or too cold? And then these orientation factors down here, separate ones for the vapor from the liquid. And we use vapor generically. It might be gas, it might be ullage, whatever you want to call it. But it allows you to define those factors separately for is it getting augmented or degraded depending on local effects like stagnations and plumes. Okay. So this is kind of a new weird world. We're presenting things that are a lot more geometric than simple 1D, but of course this is not 3D CFD. So this is what we're calling thermal-centric, basically tools that only a thermal fluid person would care about. They're special multi-dimensional tools specialized just for thermal fluid analysis. So more than a 1D flow network means that you can have knowledge of complex fluid volumes, walls, and structures. Less than 3D CFD means you are making approximations, but it's way, way faster to solve, orders and orders of magnitude faster to solve. The problems I've been showing you just take a minute or two to solve. Nothing in here is very elaborate. Taking into account the uncertainties, you have ability to adjust for parametric sizing, sensitivity, in order to be able to do many, many vehicle level transients and hopefully approach the problem somewhat statistically. So this is a key, is that this is intended for a thermal fluid engineer who understands that I can either make one run and trust it, or I can make a whole bunch of runs and hopefully take control of the uncertainties in there in order to get some real data on what's the most likely case. This has not been a training class. This has been an introduction. And so if you would like to get more familiar with compartments, of course, you need to get the 5.8 version of Thermal Desktop and FloCAD. The TD FloCAD User's Manual has a fair bit about compartments and ports. But then because this is a fairly complex system, we've got on the user forum, we have examples available for that marine tank I showed you, a full write-up of what's going on. All the models are available, that spherical LNG tank, that wrench quench problem. One that I did not show you, it's a vertical evaporator for solar thermal loop. And then another one that I did show you was the immersion cooling electronics. So a lot of write-up, a lot of examples to teach different aspects of a compartment. And there's a little bit in the Cinefluent User's Manual. Of course, a compartment is definitely a FloCAD concept, but when it comes to how these twin ties are split or how a port actually works and how you watch and see whether something is submerged or not, all those kind of things, there are more details in the Cinefluent Manual on those. And we also have tank and line modeling webinars that talk a little bit more about this too. You can watch for those in the future. And in fact, we'll have a lot more webinars coming up in the spring of the year, or at least the start of the new year in January and February, both on how to model, a little bit more training oriented. We also have a couple other webinars coming up that teach, or that introduce, I guess I should say, new concepts such as curved elements and other things that you may not be familiar with. So I'm going to pause here and ask for some questions. Hasn't been anything coming through, I don't think, that I've missed. Hopefully everyone is still there and attentive. Are there any questions? Type them in or raise your hand if you would rather me give you a mic.